Turn the TV up on top. Willem,
Yeah.
TV meant to be like that right now?
No?
Oh, there we go.
Good spot.
I just had a feeling. I was like, we never talked about turning it off. Now? Cool. When do you want us to kick off though? On the dot, so as soon as you say live. Cool.
Hi.
Yeah. My name's Prakash Sar, I'm a source of I sent a message to Joe.
Yeah.
Yeah.
Yeah, perfect. Yeah, no, join. I'll make some room for you.
Now I haven't brought my laptop.
You don't need to do them. Come to show it. Absolutely. It's straight back out, sorry. And then you tell the little guy will open the door for you.
Okay, that's why I basically head back to the main reception and somewhere in
And
there.
then straight on to the right, just beyond the elevators to the right. It's a bit of a hidden. Right, we're going to go live now.
Sure.
So, okay. Take it away, Matt.
Great. Hi everyone, and welcome to today's Real Data Science Meetup. It's great to see you all. So today's topic will be bias in natural language. I'm really happy to be here with Clara Bernstein, who's going to be talking to us all about it. As usual, we will kick off the session with a bit of an intro, a Q&A, set the scene, so I get to have a bit of fun. And hopefully you do too, Clara. And then we'll get into the bulk of the session where we'll be going through theory and demos, and we'll have sort of code to sort of step through together over the course of the session. It's going to be a lot of fun. Before we get into that though, and before we get into our Q&A, I'll do a little bit of housekeeping about what this series is. For those of you who haven't attended the Real Data Science meetups today before, they are a series of live streams and in-person events that happen every, say, 4 to 6 weeks out of London, Utrecht, Denver, soon to be Copenhagen, I believe, where data scientists from our team at PA Consulting give in-depth seminars and walkthroughs in different areas of expertise around data science, machine learning, AI. These are sort of deeply technical, hopefully very interesting, but also a way of inviting people into the discussion and creating a community. And that's really the leading principle behind why we do this series. Throughout the development of data science over time, there's always been a sort of industry and a community that's thrived in that active getting together, sharing of ideas, developing of sort of new principles, concepts, techniques. So we want to be a part of it. If you want to sort of follow the series, see when the next one's going to be, what topic it's going to be, or want to provide some feedback or suggestions for what we're going to do in the future, join our meetup network and check up our YouTube channel, which is Real Data Science, to catch past sessions and again sort of become a part of that conversation. So that's housekeeping out of the way. Now on to the fun stuff: bias in natural language processing. So again, thank you, Clara, for being with us today. I'm gonna sort of kick off with a very classic one, but it's always interesting, and I think we get a big range of responses on it. Which is, what's the path you've taken in your career, sort of to be where you are today as a sort of data science SME, giving a lecture on bias in natural language?
So my background is actually maths. So I was exposed to AI machine learning from a theoretical perspective, but less so much implementation. And I made a career change into data science because I was keen to sort of explore that implementation side. Stumbled across natural language processing just because I have a love of languages. I'm interested in the whole codification of language, and it just struck as a really interesting area for me, which was actually really timely because with the recent launch of ChatGPT, a lot of people are talking about it, and yeah, just that's how I ended up here.
Yeah, that makes sense. I totally agree. I find sort of data science around language and natural language processing, um, there's something very sort of inherent and intuitive. We all understand language, and we all sort of have our own brain mechanisms of how we process it and string things together and interpret. And it's really interesting how that becomes codified and how algorithms can get to things that perhaps aren't the way we work through that sort of stuff to enhance it. Um, yeah, I agree. One thing you mentioned there that I guess always sort of is of interest is you sort of mentioned a career change, that perhaps
Yes.
data science wasn't your first career path. I guess it'd be great to hear about that. And I guess if changing sort of career path or alley towards an industry like data science, if you think that's influenced your perspective in the field at all.
Yeah, so I am an advocate for career changes because the words machine learning, AI, NLP, all of that stuff was a buzzword that I always wanted to avoid just out of fear, really. And then from putting myself in the deep end and realizing that I actually really enjoy using that side of my brain that's like the mathsy side, realizing that it's not as scary as people think it is. And if I could do it, pretty much anyone can. But I really want to frame these conversations so that these scary sounding ish words aren't as bad, and I want to change when I'm talking about technical concepts, making it such that the least experienced person in the room will understand, and the most experienced person in the room will still learn something new, rather than just making it this sort of scary area to talk about. So yeah.
Yeah, I love that framing. I think a testament to why we love doing this series is that a field like data science, a field like machine learning, even subsets of it, there is so much room to dive into sort of
Yeah.
really niche specific areas where you can do a lot of research and sort of get to the bleeding edge, or even just sort of actually summarize what's all the stuff going on in this space. Because in the day to day, you've often got some stuff in front of you and you try and tackle it, but there'll be other people tackling different bits.
Yeah.
And as you say, like whether you're new to something, if you're totally new to something, it's great to open that door. But even if you're not new to the broad area at all, there's probably tons you can learn hearing from somebody else. That's what I find, at least. You mentioned before as well ChatGPT, and obviously we're talking about natural language today. We're talking about bias in particular. I guess could you give a little bit of a high-level summary on what ChatGPT is and why right now this is a sort of timely moment to be talking about bias in natural language?
Yeah, well, I'm glad that you asked me that because I just said I wanted to make it so that everyone can understand, and then I didn't explain what ChatGPT is. So ChatGPT, it was launched in November 2022. It's this new chatbot that uses transformer neural networks, which is a scary word, but I will be delving into what that actually means in the remainder of the session. But it essentially generates human-like text. It's the homework machine that we've all been dreaming of. It can pass medical exams, it can write wedding speeches, it can do pretty much everything. And it's based off a large corpus of language. So everything that we've fed into it, it's learned and produced something. So it's really cool. It's open source at the moment, so anyone can go on it and ask them to write a wedding speech. So, yeah.
And this all seems sort of magical, right? It's sort of like magic, as you say, the homework machine we've always dreamed of.
It is.
So, but then we've got the word bias.
Yeah.
And so I'm sure you're going to get into that in more detail, but obviously there's lots of considerations to make when something is so sort of wide-ranging, perhaps in its application. Not to spoil what I'm assuming is coming ahead. So I guess as a final question, and this is a sort of cheeky one, but we're gonna end on a high. A lot of when we talk about bias and sort of application of sort of machine learning, there's various challenges, and sometimes you hear about like snafus that go on in a high profile where something's not been sort of either validated or applied in an appropriate way, and then it's turned out doing something pretty silly. In that sort of space of like AI ethics, what can like people like us who are just sort of working away, are there things we can or should be doing? And I guess otherwise, is there anything you'd like to see more broadly in the AI ethics space?
Short answer, yes. Long answer, we will be delving into this, especially at the end. But I want to make it clear that this is something that we interact with on a daily basis in every Google search that we make, every time we make a translation, every time we use Siri. And it's so glaringly there, but not glaringly obvious. And the best example that's a really good analogy that can be translated to this is the crash test dummies that have been going on since the 50s. They've always taken the male physique, and this is car safety that we're talking about. And in an experiment at the University of Virginia, 2019, they basically put female and male dummies in a car. They put it at the same speed and crashed the car. And women were 73% more likely to have severe injuries. There was a female crash test dummy produced at the end of last year, which is quite late when you really think about it. But even that physique is a typical average woman. It doesn't account for pregnant people. It doesn't account for different body sizes. And that you can really see, I guess, how that would affect a woman in her daily life. Then translate that into Siri technology, where the author of Invisible Woman says that the Siri voice, the training data used to train Siri is 70% male voices, let alone language. And then you could translate that into other minority groups. I mean, women account for 50% of the population.
Yep.
We're the largest minority. We're not even a minority. So what will that mean for other minority groups where it's not as easy to identify? And then what I can say about what we can do about it, firstly, these types of conversations. But secondly, there's so much about this. There's so many people talking about it. You can even see when you use these products that there are changes being made. So the examples that I show, you can see that you can't see those examples anymore because they've made the update. So they are responding, these tech giants that own these products, but there's no transparency about it. And there's no, I guess, collaborative environment where we can all work together on debiasing these types of products. So, yeah.
Yeah, it's fascinating, and like as somebody who sometimes you are developing a machine learning model and you're looking at the outputs and you're thinking about things like bias, and I think sometimes it's only easy to see as far as well you can see, and it's all the more reason why in this space sort of it would be really interesting to see how broader guidelines or regulations turn up. It's also, I guess, a testament to the importance of diversity in this sort of industry and space, because having those different voices who are all seeing as far as they're seeing with regards to bias and how it might be affecting outputs of things, especially wide-ranging things that like natural language, is how you're going to start actually noticing and picking up on what could be better. Really interesting. Cool. I'm excited. With that though, that takes us to the end of our like brief Q&A or grilling interrogation, I always like to call it. And so I will hand over to Clara to actually talk us through the rest of the session. As I mentioned at the start, today we're going to sort of be a bit of a blend of theory and slides and talking and actually looking at some code and running through it, not just splitting out in two as we often do. But we're going to try and take some breakpoints just to sort of survey the room for questions or thoughts. So do just sort of put your hand up and I'll be on hand to sort of feed them in when we can. With that, thank you, Clara. Looking forward to the rest of the session. And I'll pass it over now.
Cool, thank you. So, firstly, as I mentioned before with the different examples of NLP that we'll be interacting with on a daily basis. We're going to start with Google Translate. And essentially what this example shows is a gender neutral word in Danish, which will mean partner, boyfriend or girlfriend, translated into English. And then when you add things to that sentence, the translation in English switches between girlfriend and boyfriend depending on the sentence. So you can see here that when you say my partner is a CEO, it says my boyfriend's a CEO, my girlfriend's a nurse. So boyfriend doctor, girlfriend assistant. And as I said before, if you put these translations into Google Translate now, this isn't the result that you will see. So they are responding to these types of conversations. So it's good to still have them. But it is very interesting to see what this was like. And I think the post is relatively recent. It was 2 months ago. So that's my boyfriend is ambitious and my girlfriend is passionate. So that's one example. Another example is predictive text. So you can see these are the 3 top recommendations for the next word. And we have man to follow from bright, and we don't have woman or person. Then logical, it's similar. Oh, that went very fast, but you can see person and guy, and man. And then this one. So you can see the female connotations to the word whiny. And then talking about ChatGPT, which again, I've tried and tested this, it has changed. But when you put every man wonders and every woman wonders, the output for man is why he was born into this world and what is life for. And then when you put woman in, it says what it would be like to be a man. And then another one about entering the workforce. So you can see that the answer about men is about success, businesses, and then women having sort of associations to being polite, dressing nicely, being respectful to superiors. And this is a technology that's very recently released. So if that's what's being produced now, you can only imagine what it was like just 2 years ago. Now I'm going to give a brief introduction on what natural language processing is. It's one of the many AI applications behind every technology using texts, such as CV screening, university admissions, essay grading, voice assistance, search queries, translation, and text generation, amongst many other areas. But I've chosen these examples because you can understand how, if there is bias in these products, what the effect will be on society. And what the main use cases of NLP is text classification, translation, text mining, which is highlighting the patterns of detailed information from text, named entity recognition, so this categorizes languages based on people, universities, that kind of thing, predictive text, as we've seen, and chatbots through ChatGPT. So those are the main ones. There's many others. So going back to bias and how it happens, NLP uses a machine learning, and it reveals the structure and meaning of texts for the tasks mentioned above. But in order to do this, there's a pre-stage which machine learning detects patterns in numbers. So how do we make it detect patterns in text? So that is the conversion of text to numbers, and more specifically vectors, and this conversion is known as word embedding. So word embedding is when words are represented by vectors, where words with a similar meaning will be closer together in vector space. So if we're going back to the examples, the reason why we saw those examples is because those word embeddings, so the word for man, will be closer in vector space to professions such as CEO, president, and boss, and all of the other examples that you saw before. And then the word woman will be closer in vector space to nurse and helper, secretary, than the word man. And what's important to note with machine learning is that it's characterized by the ability to become smarter without following explicit instructions. So nobody told the machine learning algorithm that this is how the world works. It picked up these nuanced patterns from the data it ingests. So that illustrates what data we're actually using, and we will delve into that further on in the session. So, talking in more detail about word embedding, so the purpose of word embedding is to make language interpretable by a machine, so it represents words in vector space based on the patterns in the data it ingests. So, if we're looking at this illustration, this is very simplified because you can see that there's only 3 dimensions in these vectors, and word vectors in the example that I use later on has about 300 dimensions, but typically you can see sort of king and queen, the relationship between king and queen, and the relationship between queen and woman, and that it's a good way to sort of visualize it in that respect. And you can see that, well, what word embedding does is encode these sort of patterns that aren't explicit but will still generate results like that. And what's really useful with word vectors is that you can use linear algebra formulas to understand the similarities between words. So the cosine similarity function assesses the similarity between vectors, and now that we've got those words being converted into vectors, you can then see the similarity between words. So this is a function that does exactly that, and from the example above, you want the similarity between king and queen to be bigger than the similarity between king and walking. So you can see that that is exactly the case. And now what you can do is you can assess bias from this function. So the bias between marital roles, the similarity between woman and wife is 56% compared to a 47% similarity between man and husband. So it's already becoming clear when we're only going 1 layer down. And then going back to the profession examples as seen in the previous example, we've got she and nurse being 47% and he and nurse being 31%. So there's clearly an association to female, femininity when you're looking at the word nurse. And then president, not such drastic results here, but still more associated to he than she. So now that's like a brief introduction on what we're going to delve into for the remainder of the session. And rather than looking at bias in the Google Translate example that we're using, we want to sort of reframe that problem into word embedding. So why are the word embeddings in such a way that you've got gender neutral terms being more associated to one of the gender specific terms? So in order to do that, we've sectioned off today's session in identification and mitigation. So firstly, we'll go through a few prerequisites so that everyone can understand what's going to happen in the remainder of the session. We're then going to go through a specific word embedding algorithm called BERT. BERT is used in Google searches, so you'll be interacting with BERT whenever you make a Google search, and it has this attention mechanism which is apparent in ChatGPT as well, and lots of other NLP models, which we'll be delving into from an identification perspective. And then in the final section, we'll have a look at a solution that will mitigate bias that can be readily adopted by these tech giants, probably on a larger scale, but also if you're individually developing an NLP model, this is just one of the many examples that are out there to mitigate bias. So going on to the prerequisites, I always found when I first moved to data science that it was quite difficult to learn how everything fitted into each other. So I thought it would be useful to sort of explain the taxonomy of the topics we'll cover today. So we have NLP, which is use case specific, and there'll be loads of other AI applications that will fit into this machine learning structure. So image recognition is another example, and we know that there's a lot of problems with facial recognition in Facebook, and this is just another example with natural language processing. So NLP is an application of AI, which is the processing of text to understand meaning. And it uses a combination of machine learning techniques, models, and algorithms. Word embedding also uses machine learning techniques, but I just thought that there'd be too many hours in this diagram, so I'll explain it anyway. But as I said before, word embedding makes language interpretable by a machine, and that's the part that we'll really be delving into. We'll be looking at BERT, which uses transformer neural networks. So then going on the top row, we've got AI, which is the broad discipline of creating intelligent machines with a number of applications. We've got machine learning, which is the ability for a computer or an algorithm to imitate intelligent human behavior without explicit instructions. Then neural network is a component of machine learning, and it represents complex data through several layers of interconnected nodes, which aims to mimic brain functionality, which is really interesting. And these are typically used when the data is highly complex because it correctly captures the nonlinear combinations between the inputs and the outputs. And then a transformer neural network is this new neural network architecture that has this self-attention mechanism, which we'll be exploring later on. So now we're going to go through an introduction to machine learning, and I'll be covering the parts of machine learning that will enable us to get through the BERT section. So there's this section alone could be a whole degree. So I'm going to keep it as simple as possible so that for the purpose of this session, basically. So as I said, machine learning aims to identify inferences and patterns in data. It doesn't follow explicit instructions, making that very clear. And you can illustrate the problem by a simple function, namely f, that takes in x inputs to produce y outputs. So y is referred to as the label, and it's the what we are trying to predict, or what the machine tries to predict. We've got x, which is the feature, so what it ingests, and then f, which will be what the machine learning aims to capture. So it's that relationship between the features and the label. So in the context of NLP, we have x being a word, a text, and then y being the word embedding, and then f being how do we convert words into vectors. And then another example, just for comparison's sake, would be the number of COVID cases. So we've already got a whole host of data of the number of COVID cases since 2020, and we can use that data to then predict the number of COVID cases in the future. So those are just two very different problems that can be modeled in the same way. So firstly, looking at supervised versus unsupervised. So supervised machine learning is when the training data that we try to learn from is labeled. So that means that we're given inputs and outputs. And then unsupervised machine learning trains on just unlabeled data. So for better understanding, the way I like to think about it is supervised learning guesses the answer by learning from examples where the answer is provided. And then unsupervised learning looks at it when the answers are not provided. So they both learn by detecting patterns, but the unsupervised method will rely on inferential patterns, such as men being referred to as positions of power. But then comparing that to supervised learning, we've got 3 years now of COVID cases to then make better predictions. So looking at NLP models, it's typically semi-supervised. So this means that the training stage is unsupervised, and then we have some fine-tuning where you adjust the parameters that will increase the accuracy of what we're receiving. So when we're looking at BERT and ChatGPT, from my knowledge, BERT has a much, the fine-tuning for BERT is a lot more than ChatGPT. Now we're going to split the problems up by regression and classification. So where y is discrete, the problem is of the classification type, So this is mainly an NLP problem. So you can see here, is the word positive or negative? What is the word embedding? What's the translation? And then where Y is continuous, the problem is of the regression type. So what's the temperature? What's the price of a house? So NLP tends to be of the classification type. And then making it very clear that by using this fx equals y, it means that the output is a combination of the input. So when we're trying to look at the word embedding for the word man, we're not just looking at man, we'll be looking at a whole corpus of training data and understanding the combinations of all of that to then output that word embedding. So we can very simplistically illustrate the combination as a dotted sum of weights and values. And then what machine learning aims to do is learn what those weights are so that the output best represents the combination of the inputs. So we're taking that problem and we are applying it with neural networks. But what neural networks tend to tackle are the nonlinear problems. So this is when we've got that dotted sum, but W and X can't be integers because the data is simply too complex. So these sorts of problems will be tackled. The neural networks will tackle problems such as image recognition and word embedding. And the idea is that it mimics the functionality of a brain by illustrating problems like brain neurons. So what does that mean? What is that illustration? This is a neural network, and it's a set of nodes symbolizing neurons organized in layers. So there's a set of weights representing the connections between each neural network layer and the layer beneath it, and then activation functions which will introduce that non-linearity aspect, that complexity aspect, where the output layer will still be a combination of the input layer, but with all these hidden layers and activation functions. So I'm going to now give a very simple example to show how neural networks work. So we have 3 inputs and we have 1 output, and we've got 2 layers in between. So each of these nodes will be a weighted sum of all of the input nodes, and then similarly the nodes in the layer above, and then the output. So you can see that this output will still be a weighted sum of the input. It's going to be split up by those 2 layers. We then introduce the activation functions to all those nodes in the hidden layers, and these are 2 examples of activation functions which are pre-known, pre-written, and you can prove that they're nonlinear. But the one that we'll be focusing on today is sigmoid, just because it returns a number from 0 to 1, so you can best see results in that aspect. You can see percentages, you can see similarities. And what activation functions does, it stacks non-linearities on non-linearities, it's a tongue twister, to let us model complicated relationships between the inputs and the predicted outputs. So it's effectively learning more complex and high-level functions over the raw inputs. So we have the neural network, we have the problem. We now want to understand how the output correctly represents the combination of the inputs. And the way that it does that is a training process called backpropagation that takes the following steps. So we initialize the weights with some random values, and then we run it right to the end, and we have that predicted output. We'll then match that with the one that we want and calculate the error. And as we'll be doing this multiple times and there'll be multiple inputs and outputs, we can define a loss function over that error. And then the idea is that we minimize that loss function by adjusting the weights. And there's optimization techniques that are applied to do that, and that will be a whole course in itself. But one of the most frequent ones are stochastic gradient descent. So this is a very typical loss function used for supervised learning. So we've got the yi is the value that we want, the y hat I is the value that we have. So we then take that away and we have that error. We square it so that it's positive, because sometimes we can have negative and positive error, and then we take the average. And then this is that function that we will be optimizing. So For the mathematicians out there and for the non-ones, please don't be scared, but this is a formula of a neural network of 2 input nodes and 1 hidden layer. So you can see that this will be the weighted sum of one of the inputs, and that will be 1 node in that layer, the weighted sum of the other node, and that passes through the value activation function and then another activation function to the output. So the main focus, so now we've got a brief understanding on how neural networks work. We're then going to focus on a very specific type of neural network called the transformer neural network, and then how that's applied and how we can see that in our day-to-day aspects. So, section 2, we are looking at BERT. So BERT, as I said before, is a transformer-based algorithm, and I've said very hilariously that it's been transformative in deriving contextual meanings of words given the inputted data. And in 2019, it was released that BERT has been used in Google search engines, and now it's in almost every English language query. So we'll be interacting with BERT every single time we want to search something online. So what BERT is exactly what it is in the name. So it's a bidirectional encoder representation from transformers. And what that means in the next slide, we've got that transformer component, which is the self-attention mechanism in neural networks, which I still haven't explained, but I will explain. BERT is of the encoding type. So transformers can be encoders or decoders. So encoders takes the sentence as an input and outs it as a word embedding. So that can be literally encoding it. And then decoders can take that word embedding and then put it back into a sentence. So you can see products like Google Translate will be encoder, decoder, but BERT is of the encoder variety, and ChatGPT as well will be of the decoder variety. Representation simply means that the output is a combination of the input, and then bidirectional, which we'll be exploring later on, is the fact that it looks at the input data in both directions. So humans obviously read, well, English humans obviously read from left to right, but this algorithm will look at it in both ways, which will have advantages that I'll explore later. So how does BERT learn? It was pre-trained on an unlabeled, so that means unsupervised learning, plain text corpus of over 3.3 billion words. That's nothing compared to ChatGPT. I think ChatGPT is 300 billion words, but you can look that online. But what that is the English Wikipedia and the Brown corpus, which I find really interesting because I've always been told to avoid Wikipedia whenever I'm writing anything remotely academic. So it's interesting to know that BERT will be using that in order to learn language. So just food for thought. And the 2 training tasks were language mask modeling. So what that means is we're taking the words and we're covering them up, and then we're asking BERT to predict what that word was, and then next sentence prediction. So this is where BERT is trained to predict if the next sentence is probable or not given the first sentence. So now we can use this mask modeling functionality to illustrate bias. Again, remembering that this is something that we'll be interacting with whenever we make a Google search. This is my favorite part of the whole session. So we have a sentence: the president went for a walk because he or she wanted to get some exercise. And what this output is the probability that that masked word will be he, and then the probability that it will be she. And this horrible error message is basically saying that the stage that this model is at is before the fine tuning. So this is just after the training phase, what those results are. So you can see that there's a staggering 99% chance that that word is going to be he, even though there's been no indication that president will be a he or a she. But as you know, it kind of makes sense. Then what you can do is you add Sweden into the sentence, where Sweden had a much better female representation in politics. And even though the he probability goes down by 0.5%, the she goes up to 1%. So there is a slight improvement, but still not that great. And then another example, New Zealander, you can see that the she hasn't really helped much, but the he has gone down. So that's really interesting, because you can imagine that the training data will be describing the New Zealander president as not explicitly a she, but not explicitly a he, which is interesting. And then German, just to round things off, again, very similar stats. So what else we can learn from BERT is that the training stage is a base layer of knowledge, and we build upon that knowledge when we're given the inputted data. So that's known as transfer learning. And what that means from a bias perspective is that we now have an additional hypothesis on where bias comes from. So we've got that training stage, and now we've got this input data part. And that's the part that we're going to be exploring now with this self-attention mechanism. So BERT takes those word embeddings from the training stage and then applies self-attention to the input data. So before I go into what it does, the purpose of it is representing each word as a weighted sum, like we've seen before in the prerequisite section, where the weights denote the relevance of all the words to the word itself. So capturing the context of the input. So when we're talking about Google, it will then understand our query a lot better from this self-attention mechanism. So I've used the example, her favorite fruit to eat is a date, because what I'm trying to get at here is that there's two meanings to the word date. So what BERT will be able to do is understand the context of the word date from that sentence. And that's the transformative part of the transformer neural network architecture. So we have an arbitrary weighted sum, but what it aims to capture that contextual relationship. So date has the highest weighting to itself, because as you can imagine, it would have more attention to its own word. And then we have favorite fruit and eat being somewhat relevant to the word date given the context of the sentence. So the weight of each word signifies the relevance to the word date, and that's what the network will be aiming to represent, that accurate representation. So then when you compare the sentence to he went on a romantic date, you'll then see that there'll be no aspect of fruit to the second example, and the word embedding will be different. And that's how you can understand why it can pick up, why it's useful, basically. One thing to add, and this is what I was referring to when I was saying the bidirectionality, is that the input data, the more words that you put in the input data, the more augmented the results become. So when you're looking at the word of focus, it becomes more ambiguous because the weighted sum will simply be larger. And the best way to understand that is when you say, I left my phone, you understand what left means in that context. But then when you put, I left my phone on the left side of the room, suddenly this word becomes more ambiguous, and it's quite clear why. But to make it clear, it's not just the word left that suffers from this ambiguity, it's all of the words in the inputted data. So what BERT does, it accounts for the augmented meaning by reading bidirectionally and simultaneously. So it doesn't just go left to right and then right to left, it does it at the same time. So that is a bias mitigation process to account for different meanings as the sentence progresses. I might stop there just because I've been talking for a while, in case anyone's got any questions before I look at the scary maths of BERT.
We don't have anything in the chat for the moment, but I'll wait to see if anything comes on in the next sort of 30 seconds or so. Got a question in the room?
Yeah, going back to that example, I left my phone in the left-hand side of the room.
Yeah.
I suppose one thing that it could do is, let's say it starts from the left end, it encounters the first instance where the word left appears. Now, as soon as it sees the second instance of the word left, it should pause it there and just look at everything before it. And then, so similarly, the right-hand side, it starts on the right, it comes up to the first instance of the word left, it allows for that. And then the moment it sees the second instance of the word left, it pauses it. So that way, it can interpreting each section as it goes along. Similarly, there's 3 instances of the word left.
Yeah.
And once it has looked at the first one, it'll take into account that result, and then go on to the second instance of the word left, taking into account what it has already learned from the first instance, look at that, and so on. So I suppose, does that also happen as well, or is it different to that?
Well, all I can say is that the algorithm doesn't know that the word is left. It's going to be looking at the word embeddings. So because BERT has different word embeddings for words with different meanings, I don't think it is as explicit as that. But then what I can imagine is that if the word embeddings are left, you can imagine that it will be closer in vector space to each other because it is the same word. So my point is, short answer, yes, that probably is the case. But due to the fact that it's all encoded, you're not entirely sure that it's explicitly doing that.
Abstracted away.
Exactly.
I love the idea though, and it makes me want to try and think of a counterexample where you can't split them up. They need each other.
Yeah.
We've got nothing in the chat at the moment, so
Brilliant.
kick on.
Cool. So we're now delving into the attention mechanism and how it works. So we've seen what it does. We're now going to go into how it does it. So firstly, we consider the input data as tokens now, because we're not just looking at words, we're looking at words and separators, and that will become clearer later on. So going back to neural networks of weights and values, we've got the weights that will now represent the context of the token in relation to the inputted sentence, and then we've got the values, which are the predetermined word embedding from the training stage, and then the aim is to reweight those values to account for the contextual meaning in the input data. So in order to do this, we need to consider the queries and the keys and the values of the tokens. So what that means is the query of each token is then compared with the keys of all of the tokens in that sentence. Those are known as scores, and they can then be interpreted as the weights of the neural network. So then the idea is reweighting those values by the scores and then taking the sum of the reweighted values, and that will then signify the contextual relationships. So if we're then going back to that same example and we're looking at the weighted sum for date, we now know that the query is the word date, and then the query will be matched to the keys of all of the other words. So this will be the query times the key of her, query times the key of favorite, query times the key of fruit. And then these words are not going to be words, they're going to be those pre-trained word embeddings. We're now going to introduce some maths again, and we're going to take 3 words as an example to explain what's going on. And I've chosen piano, music and coding because hopefully you can recognize that music and piano will probably have a closer weighting towards each other than coding and the remainder of the 2 words. So we then suppose that each of these tokens will have a query, a key and a value denoted by Q, K and B. And then we're going to apply self-attention to the word coding as an example and then expand out afterwards. So we're taking the word coding, which is with the query of the word coding, which is Q3, and then we're multiplying that by the keys of all of the other words. So you can see here we've got Q3, K1, K2, K3. We then normalize that by the vector dimension D, and that is so that the weights can then be summed to equal 1, so you can understand how that can then be compared, and it's easier to capture the contextual relevance. And then as we are working with neural networks, and that's why we went through the prerequisites, we're then going to apply that activation function, and typically it's going to be sigmoid because we want to represent the relevance and the similarity well through returning a number between 0 and 1. And then, as I said, from the prerequisites that we've got weights and values, these are now interpreted as the weights or the activated weights, and then we multiply that by the values, and in the next bit we take the sum. So just for the word coding, and with a sample of 3 words, we're taking the query of the word itself and the keys of all the other words and the values of all the other words normalized and activated. all in the wrong order, but hopefully that makes sense from the formula. Then similarly, looking at music and piano, we've got the query of the word itself, but then taking all of the words into account when computing this. We can then generalize that for any word. So again, taking the query of the word itself and then incorporating all of the word embeddings of the words in the inputted data to then best capture that contextual relevance. And that 3 should probably be n if we're using n number of words. So that was a run through of one iteration of self-attention. And in BERT, we're talking about multi-attention. So that means repeating the process multiple times. And the reason that we do that is because it's essentially to get reliable results, because self-attention can have bias to the word itself, even though it's taking all of the words into consideration. So we're trying to mitigate that by repeating the process. And the 2 optimized ways of doing this is through the main architectures, BERT base and BERT large. And they vary by the number of attention heads, so the number of times that we're doing the self-attention mechanism, and then the number of encoding layers, so the number of iterations that we have. So BERT base has 12 encoders and 12 self-attention heads, and BERT large has 24 encoders with 16 attention heads. It's very interesting when you research which one's better, because a lot of people say different things, and I really do think it's task specific. But you would intuitively think that BERT large is going to be better just because it will technically be more reliable, but it will then require more fine tuning. So some researchers actually say that BERT base is actually a lot better. And then just to finalize this section, 2 other things to take into account when we're looking at transformers is the positional encoding vector. So that's where we gather more information based on the position of the word in the sentence. So a great example to understand this is the boy rode a horse, it was fun. You can now understand a lot more about the word it just because of where it is in the sentence, and we then understand what it means. And then that feed-forward neural network, which is exactly what I explained in the prerequisites part, and it's how now the weights are learnt. So what's the point of even talking about this? This is this next part, and it basically captures the main patterns in the attention mechanism and what the attention mechanism tends to do. And it adds 2 different hypotheses as the root causes of bias. So the first one being the position of the word in the sentence, and the second one being the contextual information of the inputted sentence, alongside that third hypothesis, which is the training data set. So there are a few of these trends that show that the words can attend to the nearby words, so that positional aspect, despite the context, which can indicate a limitation to the attention mechanism and a potential cause to the bias. So if you're using an example, not all women serve men, despite the fact that this isn't actually a bias input, women might still be associated to the word serve, even though that's not what the intention of the sentence was. And then the other 2 trends or patterns that are seen to correctly capture the contextual meaning, that indicates that if there is bias in the results, maybe that's because there's bias in the input, alongside all of the other root causes to bias. So what these patterns are, we've got vertical and diagonal. So vertical is when the word attends strongly to the same single other word, and it's normally the separator token, which, well, I'll explain about that in a bit. Diagonal is where the tokens attend to nearby words of a constant offset, normally the ones immediately after themselves. The third pattern being a combination of the 2. And then block is, when I said that there's separators, if the phrase can be separated into different parts, so the boy rode a horse, it was fun, those will be 2 different blocks. And that pattern is when the tokens attend strongly to other tokens in that block itself, which can be useful because that's normally why we separate a sentence into different blocks to make sense of each block. And then we've got heterogeneous, which are the more complex, non-obvious patterns. So from those 5, you can see that the final 2 is kind of what we're aiming for. That will best capture the contextual relevance. But those ones will only attend to half of the attention heads. So that illustrates limitations of self-attention. But then the vertical pattern, that the one at the top that we necessarily wouldn't want, characterizes a third of the attention heads. So it's interesting to see that there are limitations within this algorithm. But as I said, when we're thinking about bias, it opens up the possibility for the position of the word in the sentence or the underlying bias in that sentence to induce biased results. We're now going to demonstrate that with an example. So this is an open source interactive tool called BERT, and there are links to this at the end of the section. But basically, we have 12 attention heads and 12 encoding layers, and then the sentence repeated twice, left to right, and then you can see where that attention is from the lines between each word to other words. It makes a lot more sense when you actually see it. So I've taken the example that I explained before, the not all women serve, successful women need serving. It's just an example to explain what that means. And I'm going to isolate one layer, and then I'm going to isolate one attention head. And you can see just looking at it there, that we've got that vertical trend where a lot of the words are attending to that classifier at the top. And then we've got the diagonal trend, so going down there. So if I'm then going down these words, you can see that the attention of women is towards the word serve, as I said before, even though that's not what the sentence meant. And then this one, interestingly, you've got no attention to women, even though it should have that diagonal offset. But then you do have that diagonal offset when you have women and need. So then that can give an indication that it's this training stage that's causing this to be the case. And then if I go to another layer of the same attention head, you can see from, I guess, the messiness of the lines that it doesn't really have the vertical diagonal trends, and you can see that from the separation that it might be the block one. But going down again, we've got women and serve again, even though that's not what the sentence intended. And then successful, 2 women this time, but still that women to need and serving. So that indicates the block pattern from that example. So we're just going to recap what we've been through. So far, we've identified gender bias in NLP as words being closer together in vector space, for example, man to president and woman to nurse. We've then looked at the mask modeling functionality of BERT, where you can see the probability that the word will be the word president will be associated to he or she, and then you can adjust that sentence to see how the results varied. We then explored the mechanisms behind the results, so the self-attention part, and as self-attention adds contextual information to the word embeddings, we can then conclude that any bias observed can be from either the words that we input, the positioning of the words that we input, so that not all women serve, and the training data. So that's the end of the identification part of this whole session, and we're then going to move into the solution part. We'll pause there for any questions.
So, not a question as such, but just as a sort of thinking about it, the one that's really, like, I think some things in this I was sort of very aware of before. When you think about just sort of the input data, I think like the training data, because if you're training on sort of things that have been written down, they're going to interpret a degree of history, right? One thing I hadn't really thought of was that input data piece.
Yeah.
Like sometimes how like the structure of the sentence itself will be interpreted in certain ways just by the mechanism of the algorithm. And so you could write sort of not all women serve in lots of different ways. And some of those ways would sort of encourage different readings by the algorithm, and that's really interesting. I appreciate it.
No, I agree. And just one thing to say about that is that even if it's interesting to see this as the design of the algorithm, because you can see that this gender bias problem has maybe not been taken into account in the design of the BERT algorithm, despite even, that's kind of what I was getting at.
And again, I guess, like you said at the start, it spirals way beyond just the gender bias.
Exactly.
It's been like a use case of it's cool. It's just the way it's built can encourage bias, which is fascinating.
Yeah, there's one thing I noticed when looking at the example, that if the word in question and then what I should describe as a distracting neighbouring word that's likely to trigger a bias, if it's just only a few words away, it's more likely to notice, the two are more likely to notice each other. But if they're several words away, they're less likely to notice each other and cause bias. Can that sort of be predicted? Can that, what I shall describe as closeness be described in a single manner, or is there too many variables involved? It's a bit like saying, when we have
To serve is about 4 words apart. So it's interesting that
4 is a small value in this case. But let's say if they're like 10 or 11 words apart, would it be fair to say they're less likely to notice each other, or could they indirectly end up noticing each other via other reasons?
Yeah, no, I get that. I feel like it's great that this solution is open source to test things like that, because all I did is input those sentences into the BERT-viz code, and that was the visualization that was presented. So you can actually test those sorts of things, which is really interesting.
And I guess on that point, my assumption is that if there are words that might be far apart positionally within a sentence but have very similar sort of concurrency within the vector space of the word embeddings, they're probably still going to be flagged up to a degree. It's saying these words are the same sort of thing. They're both talking about the fruit. They're both talking about whatever else. And so there's probably a bit of play between that sort of vector space embedding side of it and then the proximity and framing of the sentence itself.
Because actually I was going to say that, because let's say that you do have 2 words that are possibly up to 20 words apart, but then if, as you say, they're essentially similar in the vector space, or even more subtly, it's actually possible to perform what I should describe as a coordinate transformation, again in the sense of pure math rotations, to transform one point into another. It somehow the algorithm's basically able to generate a transformation between the 2 points in the vector space, such that they still seem essentially similar, even though they're 20 words apart in the actual text.
And I guess what's interesting about this, to close it off so you can continue, Clara, is that if those words are similar in meaning perhaps, or let's say meaning roughly, whilst they might be 20 words apart, there's a lot of other words in between them that will also be being evaluated as part of this process. And if those 2 things are sort of quite similar, they're both influencing, say, some of those words in the middle, as well as sort of each other.
So basically you have multiple arrow connections.
Exactly.
It's like a 2 to the n type problem of complexity that you deal with.
Yeah. It's really difficult. Clara, do you want to continue? Have we got anything else in the chat?
Cool. Yeah, sure.
Sidetrack your day.
No, but I think it's really interesting. I feel like your points definitely relate to each other when you're looking at the I left my phone example and then looking at the distance between the words. I feel like there's a lot more to be done in this space to really assess how it all works. But yes, our final section about a solution to mitigate bias. So this is a solution that is readily transferable to other areas of bias, but we're using gender just to keep with the story of the session, and also to show that you can take this entire bit of material and investigate other areas of bias. So in order to tackle the problem, we firstly need to categorize the language for the purposes of gender bias. So we have these gender neutral words, which are CEO and president, which we've seen to have associations to gender specific words such as well, I guess definitional pairs such as he and she, and gender-specific words such as girlfriend, dad, and actress. So bias in this case is when gender-neutral embeddings are unequally distanced between one or more of the gender-specific pairs, where definitional pairs are a component of gender-specific words. So if you consider the diagram below, we've got this x-axis, which is denoted by the definitional pairs, so the he-she pairing. And then the y-axis is essentially all the other dimensions of the word vectors. The words above the x-axis are gender-neutral words, the majority of them, and then the words below are gender-specific. So you can see the direct bias in this graph by president being in the he half of the graph, and I guess homemaker being in the she part, and that is very obviously direct bias. But then what's interesting is indirect bias, where you can see something like command and genius being associated to each other due to an underlying male association, and then on the other side, sassy and homemaker having that underlying female association. So it's interesting to section off the problem in those two ways. So the approach to debiasing is again that word vector problem, which is adjusting the gender neutral vectors, so the vectors above the x-axis, to be equidistant to all the gender specific and definitional pairs. So all of the words below that x-axis, and then all of the words to define that x-axis. So we're moving the gender neutral words to be in the middle, and then making them equidistant to all the gender specific word embeddings. So this is we're going to explain the solution firstly theoretically and then through a demo. And this is taken from a research paper, Man is to Computer Programmer as Woman is to Homemaker. So it makes sense what we're trying to do here. So again, this is open source and the links are at the end of the section. So firstly, we identify what that x-axis is, that gender direction. And the way to do that is to take a subset of gender-specific or definitional pairs and taking the space between their word embeddings, and then identifying the direction of that subspace, which will be denoted as the bias direction. So that will be that x-axis in the diagram above. And then this is the fun stuff. We have neutralizing. So that means that the gender neutral vectors above that x-axis will become equidistant to the gender specific and definitional pairs. So it's projecting the embedding in the bias direction, subtracting it from itself. So that is putting it on that y-axis. And you can see from the graph above is that when it's on that y-axis and x is 0, you're essentially removing any association of gender from a gender neutral term. So you're restoring the meaning of gender neutral to the word. And then the second part is the equalized part. So we have gender specific terms and we want to average that out, and that ensures that the gender neutral words are equidistant to all equality pairs. So a demo of this, we're going to load word embeddings trained on Google News text, and this is 3 million English words and terms, and then the embeddings in this example is the 300 dimension vector. So that's reading it. And then we are identifying the gender direction. So this is a pre-written function that computes the direction between he and she. And I feel like for the accuracy of the solution, it would be important to do more than just he and she, but you can see the results nonetheless just from doing this. The third thing is we take a list of pre-written professions. So they should be technically gender neutral words. And we are projecting that onto the gender dimension to then understand where that bias is in association to male and female. So what the script will do is output a scoring. So professions that are closer to -1 will be most male, and then to 1 will be most female. So this is representing that x-axis in the example above. So from the results in advance to seeing the results, we observe a mixture of gender-specific and gender-neutral terms in the list. with some words stereotypically associated to male or female. So philosopher is the 7th most male word. President is 101st, which I think is really interesting because of that staggering 99%. You can only imagine what philosopher is going to be if president ranking is 101st. And then nurse being the 5th most female word, and homemaker the 7th. So this is the output of the male bias words. So yeah, you can see a mixture of gender specific and gender neutral. Interesting that you've got businessman and sportsman, because sometimes you can use those words to denote women as well. So it's interesting. And then the female one. I love the socially one being the most female word. So yeah, just taking a moment to look at the results. You can see, as I said, a mixture of specific and neutral words in there. So waitress, quite rightly, is a female word. So now we're going to debias that and then compare the results. So this is, we firstly introduce some words to help us with the function. So we have pre-written gender specific pairs to help us identify the subspace. We've then got pre-written to gender specific pairs for the equalizing part, and then some to split the sample up. So this is the function itself. Well, yeah, I guess I'm not going to go into too much detail, but you can see that we've firstly got that identification of the gender direction, and then we're neutralizing in this part, and then we're equalizing in this part. I'll give you a little bit longer. And then we are debiasing the function, and what we should observe from the top 10 male and female scores is that there are, well, not should, we do observe, is that there are far fewer gender neutral terms. No, we should. Far fewer gender neutral terms in the list, as this dimension should have been removed, so that gender association will be removed from the gender neutral term. And then we're going to compare the change scores of president to nurse to link that really nicely to the initial example that we showed at the start. So looking at male, you can see there's a lot more gender specific words, but then, as I said, interestingly, maybe businessman can incorporate women as well, so it still doesn't completely solve the problem, but it's at least an improvement. And then we've got female top 10 words, which there's an interesting list, but nonetheless slightly improved. So analysing the data set changes, the percentage of female scored professions in the bias data is 45 compared to 56 in the debiased data. So you can see that there were more female associated jobs from debiasing the text, even though we probably should be aiming for 50%, but that's just the analysis of the results. Then the male scored professions goes down from 55% to 44%. And that accounts for 35 fewer male professions and 35 more female professions. Then comparing the score for president, so the bias data had a score of minus 0.056 and 101st most male. So then that decreases by 93%, that male scoring, and then the ranking reduces by 12. So it's quite a significant improvement on the score, and maybe a little bit minor on the ranking, but still an improvement nonetheless. And then comparing the score for nurse, interestingly, the scoring goes from female to male, and that male scoring increases by 104%, and the male ranking increases by 242. So that is, yeah, clearly the function is doing something. So that is, I guess, the story ending. We can see that this is one of the many solutions that we can implement to really make a change in, I guess, pre-trained bias word embeddings. So doing another summary again, We looked at examples of bias in Google Translate, predictive text, and ChatGPT, and we identified that NLP models discover hidden patterns that reflect human biases. So these biases we saw in word embeddings, and we redefined the problem as gender-neutral word vectors being unequally distanced between gender-specific pairs and definitional pairs. And then we've also got that indirect bias aspect where the words are associated to each other due to that underlying gender association. We explored the self-attention mechanism and added 2 new hypotheses to the root causes of bias. And then that brings those root causes to be the position of the word in the input data itself, and or the training data. We then look through a solution that mitigates gender bias in word embeddings, again, transferable to other areas, and that neutralizes and equalizes all those vectors so that the gender neutral vectors are equidistant to all gender specific pairs. And if you didn't listen to any of this at all, the key takeaway that I really want everyone to have is that we've got this reflective aspect and causal aspect. So we see from bias, it comes from the language that we use, and then that reflects the, I guess, issues or reality in society. But then also from the crash test example, this has a causal effect where when you're looking at NLP model design and you see that bias, it can create an instant negative effect on society by discriminating against certain social groups. And I'm now opening it not just to gender, but to all minority groups, and shaping bias associations of individuals. So this is a negative cycle of cause and effect. And to break this cycle, we need to not only make conscious efforts in our language for an NLP specific problem, but in our society to create a more inclusive society. So going back to your question, what that means for us, on an individual level, we've got a small difference to make by being conscious of the language that we use, the language we encourage others to use, and the decisions that we make. So if you're a recruiter and you're looking at CV screening, you can take into consideration what happens here to then help create a more inclusive society. We've then got those in the NLP world who might be developing these models and can embed solutions like the one I explained to make a small difference to de-bias their personal program. But then, as I said before, the big changes are in the hands of the tech giants and regulators to standardize, audit, and regulate NLP models in a decentralized fashion. So this involves transparency. So it means making their algorithms or even strategy more publicly available and opening the floor for researchers, developers, and policymakers to progress towards de-biasing. And from these conversations, there's clearly loads of people interested and loads of people that want to make a difference. And it will be a great way to do that by making it more public and open. We've then got that de-biasing strategy aspect of it. So when I said that I used Google Translate to check that the bias was still there and it wasn't, it would have been, you can see that there is a response. It would have been really interesting to have made that more obvious. And then we've got the auditing to keep these tech giants accountable, essentially. But then also, when it comes to designing these models, if we had a diverse pool of talent in the first place, maybe these issues wouldn't be so apparent now. So that's another change that can be made. And then going back to my favorite part of the session, which is that president example, even though the scores weren't hugely improved, you can see that step changes towards a fairer society can then change the results in the NLP models. And then going back to that causal effect of the NLP models, that will then change our perception of individuals and then could lead to more inclusive decisions. And then that is that momentum of a good cycle where I guess we as a society have a collective responsibility to make these changes. And that is the end.